going? What do you think?
I do.
Okay, excellent. So yeah, hello everyone. Good morning, good afternoon, good evening, wherever it catches you. My name is Martina Claude. I have the great pleasure to chair today's seminar. I am leading a research group on mineral dust at the Karlsruhe Institute of Technology in Germany. And I welcome you very warmly on behalf of the International Society for Aeolian Research, ISAR, which hosts the seminar series, which is called the Virtual Aeolian Seminars. And just to give you a few words of information on these seminars before we start, for those who are not familiar with them yet. So first, great that you made it here. And this online series is organized by ISAR in an effort to maintain the exchange between the members, even if we cannot meet personally. For example, in the International Conference on Aeolian Research, the ICA conference, which has already had to be postponed a few times, unfortunately. The online series is running since November 2020, and this is now the 4th seminar. And the next one will be announcing after this talk. So it looks like I've already seen a lot of names that I haven't interacted with in a long time. So I think this is working out really well. And today we have the great pleasure to have Bruno Andreotti present in this seminar. And Bruno is a full professor of physics at the University of Paris-Diderot. His research is really touching upon various domains ranging from nonlinear physics to soft condensed matter, hydrodynamics, mechanical physics, and geophysics. And his work is mainly curiosity driven, like he said, and is to improve basic understanding that is underlying certain phenomena in earth sciences. And just to give some examples most related to what we're going to hear about today, this includes, for example, avalanches and dunes. Bruno's work is not only theoretical, but he has also a lot of experimental experience. For example, he has in total worked done more than 4 months of field work in the Western Sahara. Bruno has published more than 110 journal articles, 2 books and 4 book chapters, and has given a number of invited presentations at conferences on a range of different disciplines, including also our last ICAR in Bordeaux. So we're very happy to have you here today. And before I hand over to you for your presentation, a few organizational aspects. Of course, like I said before, you're more than welcome and invited to switch on your cameras, at least during the discussion in the end, so that we can see one another. It will be greatly appreciated that you mute yourself when you're not speaking, such that we can improve understanding for everyone. You will have the opportunity, and I would like to encourage you to ask questions with regard to understanding of what Bruno is presenting, using the chat function already during his presentation. And then I will try to find a good timing to interrupt Bruno and ask your question. For any questions that is more on discussion of different aspects or more perspective-wise, we'll discuss this after Bruno's presentation. Either you can also already write it in the chat function, we can read it from there, or you can just ask your question orally. And if you want to, of course, ask questions orally after the presentation, I would like to ask that you use the raise hand function such that we can see who has questions, and we can also see who has had a question first. And with this, I think there's all that is I need to say for now. So I wish everyone a pleasant and informative next hour. And I hand over to Bruno. I'm looking forward to your presentation. Thanks very much in advance.
Thank you very much. So I'm honored to present something very difficult, which is what I ignore on Aeolian sediment transport. And it will take me the next 40 minutes to be able to explain what I don't understand. And in the US tradition, I will start by the conclusion. So from what I understand, 20 years ago, we had a rational picture of Aeolian sediment transport, which is based on a few ingredients. There exist one or two transport thresholds. There are two concepts called reptation and saltation. And the key ingredient is the fact that sediment transport exerts a negative feedback on the wind speed. It reduces it. And what I will show is that starting from these ingredients, the rational picture that emerges is not consistent with many basic observations, measurements. And that we need to switch to something that is not fully understood, which is based on a multiple layer decomposition of the problem that I have summarized here. At least 3 layers with very different behaviors. So that's the conclusion. So I will face a central difficulty, which is the fact that the same vocabulary is used differently in the field, in wind tunnel experiments and in theory. And I will face this difficulty by stating each time I can for each word in which context I use it. So let me start with the first difficulty, the wind velocity. So in the field, when you want record, let's say at 15 centimeters above the ground, the wind speed with a cup and anemometer, you can record something like this signal at the scale of 1.5 hours here. And it is naturally filtered at 1-2 seconds, depending on your cup anemometer. And you see that one would call this a constant wind speed in the field, while in a wind tunnel, it's not a constant wind speed. It's fluctuating with 20%. And of course, if you look on longer times, the wind speed average over, let's say, 10 minutes presents some meteorological fluctuations. And this is bad conditions for theory. So the relation between wind field work and what I will present needs to be understood with the fact that field experiments are uncontrolled. So there is a bit of averaging over different conditions in the field. So the vocabulary that I will use is rather theory or wind tunnel, in which case the key quantity is the turbulent shear stress, which is the momentum per unit surface that is transferred from the upper layers of the atmosphere towards the ground, or from the center of the wind tunnel towards the ground. And it's usually used such as to define the shear velocity U star following the following definition. So this is the shear stress. Rho index F is the air density or the surrounding fluid density, and U star is the shear velocity. Based on U star, you can define a single dimensionless number which characterizes entirely the hydrodynamic situation if there is no sediment transport. So it is the Reynolds number based on the grain diameter, which is standardly defined as the shear velocity times grain diameter divided by kinematic viscosity. So here, raw fluid divided by dynamic viscosity. This determines what I call two asymptotic regimes. In the situation where this number would be very, very small, so the grain diameter is very, very small compared to the viscous sublayer, whose thickness is set by viscosity divided by fluid velocity, then the grain will be embedded inside a giant viscous sublayer. You will see that this is the case on Mars typically. And in that case, we say that it's a smooth hydrodynamic or aerodynamic regime. In the case where the grain diameter is much, much larger than the thickness of the viscous sublayer, then it's a rough hydrodynamic regime. And dimensional analysis, it's a way for me to recall how you use dimensional analysis in physics, tells you that the aerodynamic roughness will be, if one rescale it by the grain diameter, some function of the unique dimensionless number here, which is the Reynolds number. So this smooth rough transition will appear in the following. From there, one can ask theoretically, what is the condition for one grain at the surface to be entrained by the wind, and there is a standard force balance or torque balance at the scale of a grain, which allows one to define what I will call the static transport threshold in the theoretical sense, which will not match other use of the word static. I will refer to this word only when it's referring to this diagram, so one grain and first entrained by the wind. And there is another concept which is different, and it comes, it's both used experimentally and theoretically, which is the dynamic transport threshold. Here I have plotted nice old plots by Iverson and Rasmussen in 99 Heikelt, showing the sediment flux Q rescaled by some quantity. The key point here is that it is rescaled by the cube of the shear velocity. And you see that this curve increases from some threshold here and then decay typically like 1 over the velocity. So this scaling law does not work. It does not give a flat plateau. But what interests me here is that when you extrapolate the flux to 0, this would define here a dynamic transport threshold at 0.2 meters per second. On the right, I have replotted the Keld measurements. So there are a little bit less points. I think it's only for the flat when the tunnel is horizontal. And here I have rescaled only by the velocity squared, and you see that it exhibits something like a plateau, so a scaling law of the saturated flux as the squared velocity. And again, you can extrapolate it to 0, and you see that there is a problem here of the extrapolation, but it's really defined like this to find the dynamic threshold. So these are two of the important concepts. Okay. If I consider the static threshold only from a theoretical perspective. Yes, tell me.
Oh, no, I think someone.
There's some noise behind. Okay, so if I consider the static threshold problem for from a theoretical perspective, then the dimensionless number which can be constructed to measure to compare the shear stress rho fluid u star square to gravity is the Schill's number, which is defined this way if I have not done a mistake when copying it. And there is a unique control parameter, which is, say, the grain diameter. The threshold depends on the grain diameter. And to rescale the grain diameter, there is a unique combination of gravity, viscosity, and the density of the particles and the density of the fluid that produces a dimensionless number. So this dimensionless number, you can understand it as being the Reynolds number of a particle falling in some fluid under its own weight. In other words, if you here compute what would be the value of U star if I impose a constant Shields number, U star will be square root of rho p minus rho f GD over rho f. I replace it in the formula for the Reynolds, and it would give me the Galileo number. And from pure theory, from simple mechanics, you expect a unique curve for the static transport threshold relating the Shields number versus Galileo number. Large Galileo number means large grains, and large grains means rough aerodynamic regime. So I will take a laser. Yes. So this here is the rough regime at large Galileo number or large grain diameter or small viscosity. All this is the same. And at small Galileo number, so small grain diameter, you enter the smooth viscous aerodynamic regime here. In both asymptotics, you expect constant Shields number to be selected, and there is a transition between the two. And you can close your eyes and predict this curve to define the static transport threshold, which means that if you find that measurements do not fall on this curve, it cannot be called static transport threshold in the theoretical sense. Third ingredient, when grains that are transported by the wind impact the ground, they eject other grains, and this has been called reptation traditionally in the 20th century. Oh, by the way, this is a numerical simulation that I will use later. From these ingredients, we can build the basic model that I will then criticize and partly destroy. So the key point, the last ingredient is the negative feedback of sediment transport on the wind. What I mean by that is that each time a grain is accelerated by the wind, it exerts, the wind exerts, the fluid exerts a force, a drag force, which accelerates the grain, and the grain exerts in turn force on the fluid. So that acting on the fluid phase, there is not only the viscous stress and the turbulent stress, but also a particle-borne shear stress, whose expression is there on the average. So the momentum which is exchanged between the fluid and the particle is, so the momentum is the mass times the horizontal velocity. The change of momentum of a grain is the difference of, is the mass times the difference between the velocity when it arrives on the ground minus the velocity when it was ejected or rebounding on the ground. And if one multiplies by phi, so phi here is defined by this small diagram, it's the mass of grains that are leaving the ground. For the moment, I don't want to be more precise, per unit surface and unit time. So it's a vertical flux, and it has the units of a mass times a velocity. And the Q here that I have used before is the horizontal flux. So it is the mass of grains transported from the ground to infinity in the vertical direction per unit transverse width. So if I consider only one type of trajectories, it simplifies the description a lot. And that's the one ingredient of this rational picture. And I will call A the hope lengths. And then there is a simple relation between horizontal flux and vertical flux. Horizontal flux is A times vertical flux. And the grain-borne shear stress is the exchange of horizontal momentum per unit surface due to transported grain, and it's simply the vertical flux times this velocity difference. The shear stress partitioning, I don't remember if it was introduced already by Bagnall, but I usually refer to Owen 64 for this derivation, tells that the total shear stress, which is the momentum per unit surface arriving from upper fluid layers towards the ground, can be decomposed into the fluid part and the particle-borne shear stress. From there, you naturally deduce, but it took almost 40 years to do this in a self-consistent way. You conclude that if the transport layer is localized over a certain thickness, let's say 1 centimeter to fix ideas. So here I have plotted the vertical axis z divided by grain size versus horizontally the velocity rescaled. So these are velocity profiles conventionally plotted. And inside the transport layer, the wind, even when U star is increased due to the increase of the sediment flux, the wind is reduced and more or less reaches a profile which is independent of the wind strength. So this is very this is the key point of the talk in some sense. So it has to be very clear that in this picture with a single species, the negative feedback of sediment transport on the wind implies that in the transport layer, the wind is reduced always to more or less the same velocity profile, which has a consequence, and this consequence is that all particle trajectories taking place in this transport layer must have properties independent of U star. They must fly always the same independently of the wind strength. So to close the model that I will later criticize, one needs a saturation condition. At what condition is there balance between erosion and deposition? And this is called the saturation condition. And a conventional criterion is to say, well, if you increase U star, the shear velocity, then the number of particles transported increases in saturated conditions, and erosion of the ground or ejections of new grains will stop when the fluid-borne shear stress will reach some threshold value that by definition will be what I referred previously to as the dynamical threshold. If I impose this condition that the fluid velocity decays to its threshold value at equilibrium in steady state conditions, then you get a close expression for the number of particles leaving the ground per unit surface and unit time, which goes like U star square with V down minus V up being the typical difference of horizontal velocity for one grain flying in the transport layer. So in using this type of numerical simulation, so the different groups have now used standardly this kind of simulations. The wind is described and the grains are described one by one with the contact mechanics. And in this kind of system, you can test precisely one point. Do we understand sufficiently the microscopic ingredients to recover some observed laws? For instance, is it important that particles are not spherical? Is it important to describe friction between grains by a very simple law like Coulomb law of friction, etc.? Is it important to be in 2D or 3 dimensions? And what we observe in such a simulation is that this law that is derived from the rational model of the 20th century is perfectly obeyed. So it is very nice, relating the vertical flux to the Shields number. So Shields number, I have not replaced it here. And nonetheless, it works, but when varying the density ratio between the particles and the fluid, so this can be either done by changing the fluid, like going on Mars, or changing the density of the particles, the same law is obeyed without any problem when going to air to even water, so density ratio 2, which is amazing. So do we have a direct proof that there is negative feedback of the sediment transport on the fluid? The answer is yes. You can measure it through the aerodynamic roughness. So here I've not called it Z naught in order to avoid confusion, but ZS for saltation. And these are again measurements by Iverson Rasmussen 99, if I remember correctly, showing that the hydrodynamic roughness increases like with the shear velocity u star. And if you use a simple model saying the wind velocity profile remains the same in the transport layer, whatever the value of u star, of course, above the transport layer, the velocity profile needs to readapt to the fact that you extract momentum in this layer. Then you can produce a simple law predicting the value of d naught, and this is the black curve. So it works perfectly. So let me summarize what I call the 19th century rational model. You can understand everything with a single type of trajectories to idealize the problem. And the key conclusion is that inside the sediment transport layer, the velocity is reduced to its threshold value so that the grains that are transported, that are flying, that are saltating, their properties should not depend on u star. That's the key conclusion. The second conclusion is that because the properties of the grain should not depend on u star, the saturated flux should scale as the squared shear velocity and not as the cube shear velocity as predicted initially by Bagnall. And I have already shown you that this was roughly obeyed by the data obtained by Iverson Rasmussen and many other groups. Third, impact ripples, they are produced by these grains that are transported in the standard picture. They eject other grains, so that if the grains that are impacting the ground do not have any property beyond their number, depending on the shear velocity, then impact ripples should have all their properties independent of can be performed. And I will add two questions. One is hidden here. I don't know why. So the first is a problem of understanding. In the shear stress decomposition here, in the shear stress decomposition, one says, well, the wind velocity in the transport layer is reduced because grains are transported and take some momentum coming from the upper layers of the atmosphere. And then the next point is to say, well, equilibrium is reached when the fluid is not any longer able to transport particles at the surface of the bed. However, the total momentum arriving to the ground remains the same. It's just the way it arrives on the ground that changes. It is carried both by the grains impacting the ground and by the fluid. So why have we said that saturation condition was this one? This I consider is a difficult question and even an open question. The hidden question is the following. I have started with two concepts, one theoretical, the static threshold, transport threshold, and one applied in the field or in a wind tunnel, the dynamic transport threshold obtained by extrapolating to zero the flux curve. If these values are different, it is standardly said that there is the so-called transport threshold hysteresis. And the question is there such a hysteresis? And is it clear that there is one? So let's start by this series of tests and questions. And the first thing that I would like to show is results from numerical simulations. I've showed you that some of the observed properties are obeyed in the numerical simulation. We will see more later. And here I have just plotted the saturated flux rescaled by shear velocity squared as a function of shear velocity. And the black line here is the expectation from the old rational model. It should go to a constant, and one observed that at above 3 times or 4 times the threshold, when at very high velocity, one sees a nice straight line, so that the flux goes like U star cube ultimately, as predicted initially by Bagnald. The reason for this is that actually the approximation that there is a single species, a single type of trajectory is violently wrong. There are many types of trajectories, everybody knows this, so that in particular, there are grains flying above the transport layer. And when they fly above the transport layer, they enter a zone where the wind velocity again increases with U star, which is not the case inside the transport layer. And here I have plotted in a numerical simulation the altitude Z rescaled by grain diameter. So this is 20D. And here it's the average horizontal particle velocity. So this shows that inside the transport layer, which is defined by the zone in which the wind is reduced, the particle velocities are as expected, independent of U star, but above there are some grains flying in a free wind, an undisturbed wind or almost undisturbed wind. And when this particle become dominant, this is the case at large velocity, well, they dominate the scaling law, and this provides this part of the curve. While close to the threshold, the sediment transport is essentially localized inside the transport layer. And now you see that I need to change name. This should not be the transport layer, but the feedback layer. And I will call the upper layer a free wind layer, because it is essentially undisturbed if you ignore the fact that the roughness changes. So already there we see that we need 2 layers, but at least what I've presented before describes very correctly what occurs in the first centimeter scale layer, which is the feedback layer. Now I go to ripple characteristics. if now that we are convinced that in the feedback layer, particles are transported, grains are transported with trajectories that are independent of U star, one would expect the ripple emergent wavelengths to be independent of U star. And this is violently wrong, both in the field and in the wind tunnel. These are wind tunnel experiments where I have reported the wavelengths in millimeters. The grains are, if I remember correctly, around 100 microns. And you see that the trend is roughly linear and almost vanishes at the threshold. It does not, but if I would describe in a phenomenological way the curve, it would be this. So this is a real giant problem in the description, because it should not be like this if the feedback layer is a correct, sufficient picture. For the propagation speed of ripples, it's a bit different, because of course the propagation speed depends on the amount of particles transported. The larger the number of particles transported, the faster the propagation speed. But again, the scaling law is not at all the one expected from the emerging picture at the end of the 90s. So in the recent period, we have performed experiment in this very nice low pressure wind tunnel. It's the only work I have published in the last few years on Aeolian transport. And we have measured in this wind tunnel the properties of impact ripples as a function of pressure. And here the curves are for the same ratio of the shear velocity to the threshold. So in this case, we have fixed the ratio to 1.5. So we are 1.5 above the threshold, whatever the pressure, and we decrease gradually the air pressure in the wind tunnel from 10 to the 5 Pascal is ambient pressure, and gradually we decrease the fluid density. And what you see, so you may notice that the wavelength in the picture is not the same as the one reported. This picture is taken just above the threshold. It's 1.1 times the threshold, while the curve is 1.5 times the threshold. And what you see is that when you decrease pressure, when you go to Martian conditions, essentially you see nothing. It's a flat curve. So the emergent wavelengths for a fixed grain diameter is independent of the fluid density at constant U star over U threshold. The bottom curve shows two curves. One, the red points are the overall erosion of the bed. It's a short wind tunnel, few meters, 3 meters if I remember correctly. So it's pretty long, but not sufficient to avoid erosion, overall erosion of the bed when pressure is decreased. So when the fluid density is decreased. And the overall erosion remains roughly the same when we decrease the pressure. And the propagation speed, which gives an indication of the sediment transport, as I said before, is also almost constant. So it's a kind of strange negative result. Nothing occurs, and in particular, we do not see any signature of a possible giant saltation trajectories which would induce giant ripples. In this case, they are gently 10 millimeters to 15 millimeters wavelengths. So what we did to try to answer this question, why do we see that emergent wavelengths of impact ripples depend on wind strengths, why they should not, if the picture is correct, is to use again numerical simulations. We were absolutely not sure that we would recover the correct scaling laws because we describe turbulent fluctuations, we ignore turbulent fluctuations, we use some hydrodynamic reduction of the problem, etc. And so we were lucky enough to find that in this reduced model, the ingredients are sufficient to recover that the wavelengths increases roughly linearly with wind strengths above the threshold. And the points that you should look at are the violet points, the red points are the lab measurement of true ripples. And same for the propagation speed. So what does it mean? It means that the discrepancy between standard picture and reality is also present in the numerical simulation in silico, so that we can perform measurements to understand the origin of the discrepancy. Oh, I forgot to send the movie. So here you can see the simulation with the grains that belong to the feedback layer, now that I call it. They are mostly arriving on this zone of the impact ripple, and are producing a lot of ejection localized shear that will produce the instability. So we come back to a flat ground and we measured the vertical flux of particles. It is plotted here, measured as a function of height. The dotted line here is the position of the static layer, the surface of the static bed when we started the experiment. And this vertical flux is for each layer. For instance, if I choose 5 grain diameters here, we count the number of particles crossing per unit surface, unit time, the horizontal surface here. And the difference, the plots are the same data for different wind speed. Red is close to the threshold, blue is far from the threshold. And here the flux is rescaled by U star only, or U star minus U threshold. And here the flux is rescaled by U star squared as expected from the rational picture of the 20th century. So first we need to look at this graph. What does it show? It showed that above the bed, it works. We have a collapse of the curve in this region, but actually it starts only at 1, 2, 3 grain diameters from the ground. Well, maybe 2 grain diameters from the position of the static bed. Above this, it behaves more or less as we were expecting. However, inside the bed, in the superficial layer, which is 3 grain diameters, there is a giant vibrations. There are giant vibrations of the particles, giant vertical exchange of mass taking place. And you see that there is not any longer any collapse of the curves. If on the opposite, I rescale just by U star, then phenomenologically, we see that what we observe in what will be called now a superficial layer, we get a collapse of the properties. So this means that in the region where collision take place, there are lots of collisions between the grains, and these collisions are excited both by grains impacting the ground and the fluid drag force on the surface. This difference between the two curves means, and I will insist a lot on this, that the splash function that I have not discussed yet, the splash function is the idea that when one saltating grain impacts the ground, it will eject other particles. And if you have twice impacting grains, it will eject twice particles. It means that the splash function concept is additive. The number of ejected grains is proportional to the number of impacting grains. They are all acting independently. The fact that the scaling law expected is violated means that the superficial layer does not behave at all like expected from the splash function theory. The grains in this superficial layer, if I have to give a flavor of what it could be, behaves more like a gas-like layer where the particles are agitated and make a lot of collisions with collective effects. Collective effect means non-additive effects. The number of grains ejected is not proportional to the number of grains impacting the ground. This lack of proportionality is the key point. On the right, I have plotted for the upper layers, this one, and for the lower layers, that one here, the distribution of hope lengths as a function of length. So this is strange variables for the distribution. And in the upper layers, the hope length has a probability decaying exponentially. However, in the superficial layer, this very strange layer, which is 1 or 2 grain diameters in thickness, the distribution is a power law like 1/L. And this is in physics, a distribution like 1/L is a signature of something, because it's a strange distribution which has no average. It cannot even be integrated 1/L, so that you know that there will be some cutoffs at large L, small l. And this usually what is found in critical phenomena. But I don't want to insist on this aspect, just to destroy the splash function concept and introduce the fact that there exists in numerical simulations for the moment a superficial layer with different properties, and these properties can be characterized by this vertical flux in the superficial layer, which scales differently from the flux above the superficial layer in the feedback layer, and the wavelengths that emerges for ripples scales like the ratio of horizontal flux to the flux in the superficial layer we found on a phenomenological way. So I will go fast here. I send you back to the paper. I don't want to insist any longer, but just give you my own conclusion that after having rejected the old model, we are for the moment not able to provide an alternative explanation, but just a description of the things that were not correct previously in the model. So I arrived to the last point of the talk, which is the question on the sediment transport threshold. So what we did with in the the low pressure wind tunnel is to use a very precise method to try to measure the sediment transport threshold going from Earth conditions to Mars condition and below. The precise method is the following. So normally it's a movie. Let's see. Yes. So we use the microscope, which allowed us to visualize sediment transport in a centimeter scale layer. So it is not the superficial layer that we image, but truly the feedback layer that I have discussed before. And imposing the fan velocity in the wind tunnel, it is a recirculating wind tunnel. This may be very important, which means that grains that leave the wind tunnel, they may be casually reinjected at the entrance through the closed loop circuit. So we measured, we used, forgive me, we used this, oh, I would like to resend the movie, so it's not a problem. So we used this microscope picture, and we calibrated the number of red pixels in this zone associated to one grain in order to estimate, by just averaging the intensity of light in a certain zone of the image divided by some constant, gives roughly the numbers of grains transported. And we measured it systematically as a function of wind speed previously calibrated for a given velocity. So this is measured in Martian condition, if I remember correctly. And we see the number of grains that we visualize on the microscope image, function of velocity. And what occurs here in a small velocity region is that we observe individual grains flying from time to time, every 2, 3, 10 seconds, sometimes 40 seconds. So, of course, below 1 grain per 10 minutes, nobody will curious about the existence of this transport, but it was very strange because we could not find a situation where truly there was no individual grains transported. And above some crossover localized here, then we start seeing some bursts of transport, not a single grain in the microscope window, but 2, 6, 15, etc. And extrapolating down this linear curve to 0, we define some kind of dynamic threshold in the sense that I have previously defined extrapolation of a dynamic curve. And in this case, we increased the velocity, decreased the velocity, and if we wait for a sufficient time to prevent some possible transient to get casually a situation where 1 grain is entrained, we measured the same properties going up and down. So no hysteresis, reason for which I have removed the S in threshold and call it threshold, the threshold. Of course, it's not a threshold, it's a crossover between two regimes, intermittent regime, burst transport regime. This, in physics, this kind of situation where below a crossover, you see still some signal is called imperfect bifurcation. It's typically what you find in a system where there is thermal noise or any kind of noise. So here, there is a source of noise. The wind is turbulent, and if the wind is turbulent, then whatever the value that you impose to U star, there is a probability that locally you get some momentum going to the ground, which is large enough to destabilize one grain and get one grain entrained. And in an imperfect bifurcation, you can never see perfectly static. Of course, you can if you go to very, very low velocities, but in the neighborhood of the crossover, you still get few grains transported, and it is normal. It is due to the noise. Second remark, if would I try to find what I called the theoretical static threshold, which is defined by this force diagram, then it cannot be, it is strange to find it below the dynamic threshold. Why that? Because normally what is called hysteresis is the following. You increase the velocity and entrain the first grain here, for instance, and then this entrained grain will eject other grains in an exponential increase, and you will reach the dynamic state. And once grains are entrained, you decrease the velocity up to the point at which the transport is not any longer able to be sustained. So a static threshold would be here in the sense that I have defined. So would you measure a static threshold the last time here where you're able to entrain individual grains? It would not correspond. It would be perfectly defined from the experimental point of view. You are perfectly allowed to call it static, but it would not correspond to the static free body diagram presented below. The two concepts become separated. So where are the points obtained by this procedure, which is now well defined? So our points are for the moment, the five dots here, which are obtained at close to ambient pressure. So let me introduce you this strange representation of the threshold. So this is the shield number at threshold. Horizontal axis is the Galileo number. So essentially it's the grain diameter if you change only the grain diameter but not the environment. On the right, you have the rough aerodynamic regime. On the left, you have the smooth aerodynamic regime. And I have represented data obtained in water. In water, there is no splashing. There are no ejection of grains, so that it resembles what would be the curve corresponding to what I defined as the static transport threshold in the theoretical sense. And actually, if you superpose what is predicted from mechanics, it agrees very well. So in this region, there is a little bit of cohesion in the experiment, and we introduce it in the model as well. But what I would like to stress again is that in any environment, a threshold which would coincide to this free body diagram should fall on this unique curve, whatever the density ratio between the particle and fluid. What we measure, what has been measured in the literature, summarized by these squares here for different grain diameters, you see clearly that they are below the prediction for the static threshold and below the values obtained underwater, which means that all these points, some of which were referred to as static threshold in the experimental sense, are not at all static threshold in the theoretical sense represented here. And you see that with our definition here, actually we are precisely on the curves obtained in the literature. So it is much more quantitative, but not different from what people have done in the past. in the low pressure wind tunnel, this is the surprise, last surprise. So we started at ambient pressure with a given grain diameter. We decreased the pressure gradually, measured the dynamic transverse threshold, which is a crossover between intermittent regime and burst regime. And the black line, I've not discussed what it was here. This was the green line here. It's a model of dynamic threshold based on the 20th century simple model. So a single trajectory represents the whole transport. And so it's nice because it was calibrated to match ambient pressure. And for a while, we observed that prediction was correct. And suddenly at low pressure, we observe deviation. And these are raw data, so no interpretation in the data. It's close to what we measure. So we see a reduction of the threshold velocity at low pressure. Low pressure in dimensionless numbers is large density ratio raw particle over raw fluid, which is the thing that we started to change rather than grain diameter. This is the last slide with results. I have represented in the diagram Shields number, Galileo number, all the data available that can be compared. So with the same definition of the threshold, this is water, squares are the Aeolian data from the literature. The triangles are Greeley in the 80s, changing the pressure, and our data are here with the strange zone. And here I have plotted for different grain diameters, both our data here, but also Greeley data there. And you see that varying the grain diameter changes a lot the curve. They are not almost collapse any longer. There is a giant dependence in the smooth hydrodynamical regime here, or in the very large density ratio regime, a strong dependence on grain diameter. I have no explanation and no theory for this. So that's why it's at the end negative results. So what we propose is to change the four concepts initially introduced: reptation, saltation. I don't use the same word because otherwise it would be a nightmare, into a description in layers. So a static bed, collisional layer, which looks like a gas and where collective effects take place, non-additive effects. The feedback layer, which at the end resembles closely this old picture, and free wind layer, which is even simpler because it resembles the Bagnall picture with grain flying with larger and larger hope lengths as shear velocity increases. Lucky enough, the feedback layer, which was the central model, controls some of the transport properties, and in particular, the saturated flux close to the threshold with the U star squared scaling. So the old model allows one to get some of the replies when this layer dominates the quantity that you want to understand. Third point, the splash function does not exist. It's a very bad concept because the collisional layer is not at all the sum of the ejection produced by each grain colliding the ground. It's a zone which is highly non-additive, where there are collective effects. In the collisional layer, we find in the numerics some scale-free properties, this strange distribution that hope lengths has a distribution going like 1 over the hope lengths. And this was never investigated experimentally, so I'm not entirely sure that it will survive when people will start doing true experiments there. Next point, the statement that there is a 20% hysteresis in Aeolian sand transport is now very strange to me, because none of the reported sediment transport thresholds coincide with the static threshold in the theoretical sense, which can be calibrated in water. It is always far below. So one conclusion is that transport threshold hysteresis must be revisited using more quantitative objective tools, both in the fields and in wind tunnels, in order to clarify the concept. Next point, we don't have any reduced model for dynamical threshold. It is not correctly understood because it requires to understand the collisional layer, which is itself not understood, in the sense that there are no existing reductionist models that work correctly and allow one to get a satisfying simple picture. And last conclusion, the idea of changing continuously the density ratio between particles and the fluid that we have used in the low pressure wind tunnel is an interesting way to open an experimental box, which of course is not feasible in the field, but has some consequences for planetary research on sediment transport. So thank you for your attention.
Thanks very much, Bruno. I was looking for the clapping hand feature. I think that's been an excellent presentation, and even if we ran a bit over time, I appreciate that you really took the time to explain things very thoroughly. So thanks very much for that. And this is actually proven by no one asking understanding questions in the chat, so there was no need to interrupt you. I'm sure there's questions now, and I see Thomas wants to start. Please go ahead. And I would like to, yeah, like you do, encourage everyone when you ask questions that you actually switch on your camera so that we can see you.
Hello, can you hear me?
Yes.
Yeah.
Yeah, okay. So I very much agree with what you said in the first part of the talk, especially about the collisional layer. And I want to point out that we published a paper in 2020 where we showed that this collisional layer is actually responsible for why the scaling of the mass flux changes from U star square to a higher U star power. And it's actually power 4, not 3. And this has to do with collisions between particles. So very much like you say, it's a gas-like layer where you have binary collisions. That's one of the comments. Then the second comment I have is about hysteresis. And I do agree with the notion that it's difficult to speak about the hysteresis between a static and a dynamic threshold. But I would like to say there is evidence that there is a hysteresis between two different dynamic thresholds. And I could show this if I'm allowed to share my screen. Is this okay?
Sure, if you're brief, then go ahead.
So this is just a plot here on the right side from my recent paper. And I pointed out two thresholds, theta C and theta T. So both are, the lines are models corresponding. This is a line for the model for capturing theta C, which is what I call the continuous transport threshold, is a dynamic threshold. And the other one is a line for theta T, which is what I call the impact threshold. And there is hysteresis, and the model actually reproduces your data, including, at least consistently, there is an increase in the data in the beginning, like you have as well. So, and I could explain more about this, but I leave it to the others. Okay. Well, so I leave it. I mean, I have more comments, but it's enough for now, I guess.
No, I will not. Well, thank you for your comments. As I said, I don't have a clear picture myself, so it's normal that research will go on before we reach a new consensus. So I I appreciate the fact that you already contributed to build a new picture. I take caution on what I say today, because
Okay.
when you see already the change of perspective over 20 years, I would bet that we will have strong changes in the next few years. So
Okay.
I will keep my distance, the distance that I took during the talk. Of course, I read what you what you wrote before. Yeah.
Thanks very much. Other questions? I'm sure there's more questions, no? What? Oh, right. There was a question in the chat which didn't pop up in my screen. Thanks for pointing it out, Mike. Peter Rawrens, I'm sorry, I'm probably mispronounced your name. Thanks you for the presentation. And he comments, I will just read it out to you. You have neglected turbulence at most. However, in the wind tunnel, the flow is turbulent. What's the effect of turbulence? Do we need more research to include the turbulence statistics?
So the logic of what I have discussed is to look at each quantity that we are able to measure independently of each others, because they are not all sensitive to the same dynamical mechanisms, to the same layers. So from there, if some of the quantities are the same, follow the same scaling laws in the field and in the wind tunnel, then I would safely say that in the reductionist approach, you don't care that much in the explanation. It may change some quantitative values. So for instance, for the Aeolian impact ripples that we have been studying both in the field and in the wind tunnel, we could not find any signature of anything being different in the field and in the wind tunnel. So now for the last part of the talk on the threshold, where we could not find any threshold due to the presence of noise, then the fact that the wind conditions fluctuate more in the field than in a wind tunnel become important, because you explore what would be in a wind tunnel different shear velocity conditions. So in that case, it's fundamental that there is noise. There is probably already noise in a wind tunnel. And this would change the first entrainment criterion below the dynamical threshold. So again, the answer would be, I don't know, because my whole logic was to pose open problems. So if there are such big part of the problem that are not understood and that's for the moment required to destroy all concepts transiently, then maybe, I don't know.
Thanks very much. And the next question comes from Andreas.
Yes, hi, good morning, Bruno. Thanks for that great talk. I really enjoyed that. Some really exciting results that you found there. And I think it's really exciting because the best research opens up new questions. And I think what you've presented this morning definitely poses some new challenges to us to deal with. And one of the questions I was thinking about is whether these new findings on the dynamic transport thresholds in different pressures and different density ratios. What sort of impact could that have on ripples that we observe on Mars? Would we expect anything different in terms of their characteristics and their behaviors, their wavelengths, their celerities? Would we be able to learn anything from observations of ripples on Mars?
So what here I will state a very precise claim and do not claim anything but these precise claims. We have measured impact ripples in the wind tunnel there in Martian conditions. So Mars is somewhere here. So we observed them and we were able to track them by slowly decreasing pressure so that we're sure that the same object. And at least for their emergence, it's amazing because we see a new regime emerging for the threshold, but we see absolutely nothing on the ripples themselves once we take a constant U star over U threshold. So you may say that this is not logical, that because impact ripples should reflect the superficial layer. I do agree, it's not logical, but that's what we observe. It's raw data. Then you can argue as well that because this wind tunnel is 3 meters long only, well, only it's what it is. It is not long enough to reach saturated transport, so that these ripples that we measured, they were in overall erosive conditions. So my interpretation is that because we observe impact ripples that have properties independent of pressure at constant U star over U threshold, this must be interpreted as the fact that they do not know about the upper layer, the free wind layer, the Bagnolsian trajectories, the very long one, the giant saltation of Mars, which does exist. It is not involved in the equilibration of impact ripples. They equilibrate much faster. As soon as the feedback layer is equilibrated, we get these properties. So beyond that, I don't want to bet on the future. We need to find tricks to saturate transport in such low pressure wind tunnels, which is a problem in itself.
Thanks very much. Are there other questions? I have one myself, in fact. Commenting also on the perhaps trajectories of saltation particles and their length. What if for the very large trajectories, the particles actually leave the saltation regime and enter into suspension? What is the impact of that in terms of, say, impacts back on the ground, which may be missing, and any interaction feedback mechanisms? Do you have any thoughts on that?
Yes, absolutely. So this is important. Let me go to the. So here, this is the only place where we could find the signature of the particles in the free wind layer above the feedback layer. And they become dominant indeed in at velocities where fluctuations could be important enough to produce turbulent suspension here in the upper layer. So this cannot be reached in the numerics because we do not include the turbulent fluctuations. So it provides a better reply maybe to the previous question as well on the importance of fluctuations. Indeed, we do not have, I don't know if anybody has included this in numerics, but we don't have in our numerical simulations the possibility to get in the upper layer suspended load, which certainly would modify all the equilibrations, but at least close to the threshold, it's not the case.
Okay. Any last questions, Bruno? If not, then I thank you very much again for your presentation. And before we close now, I would like to announce that we have our next virtual Aeolian seminar coming up by Jibei Ju from Nanjing University, and that is going to take place on 9th June at 4 p.m. China Standard Time, and that is, if I looked it up correctly, around 8 UTC. And the topic will be dune beat stability and critical transitions in Chinese dunes during the past 12,000 years, so quite a long time period. So I'm hoping that, again, we'll have an excellent seminar next time. I think this time we really had, and we're touching upon many fundamental physics aspects that are relevant for, well, basically all of the different research aspects that we're typically tackling. So thanks very much again. And then, yeah, looking forward to seeing you again soon.
Okay, thank you very much. Bye.
Thank you, bye-bye.
Bruno, can I make a comment?
What?
Oh, yes, microphone shut down.
Bruno, thank you very much on behalf of the board and Jan Barand and myself and Martina. That was really a fantastic talk. I'm left troubled though. It's been relatively straightforward to teach reptation saltation to undergraduate classes. It's not going to be so easy, or if I do, I'll know I'm lying. I did wonder about splash saltation that was driven by raindrops. That is a different process, of course. But yeah, it's a wonderful talk, and I'm very grateful.
Thank you. I apologize for the disturbance. I myself spent years being disturbed starting from the same picture. So
I think Andreas summed it up very well. Good research leads to the need for the imperative for much more good research. Well, I'll say good night to you, Martina, and good night to you, Bruno and Frank and others. It's bedtime. I've got to go home for a start. So
Right.
Thank you once again, okay?
Yeah, from me too. Thanks, everyone. And